All right, what's up, guys? We got another long one, 330. We have to determine U1 and V1, right? And the stresses in each element. I'm gonna keep it short. They give us E, A, and L for each bar. So let's go ahead and get started. All right, so we know this is the stiffness matrix for 2D elements, right? In the X and Y direction, we got 3 elements. We got this bar, this one right here, and number 3 right here. So 1, 2, 3. So again, we do this table to kind of gather all the information we'll need. For now, we'll need the C squareds, right? The C squared, S squared, CS to make this matrix right here, and the EAL. But we will also need cosine and sine to find the stresses later on. So you'll see. So yeah, determining the angle, I mentioned it in the other videos, but moving forward, I'm just gonna mention it every single time. So you know there's the positive X direction, right? And we want to find an angle to kind of characterize each beam. So it's like, I always like to start from the small node to the big node. In this case, right, for element 1, we're going from 1 to 2. I'll tell you which angles to use, right? So if you want to go from 1 to 2, your x-axis, your origin's right here, right? There we go, up and down, left to right. So that means it goes up 90 degrees. So this angle for us, it's gonna be 90 degrees, but we have to take into account that it goes from 1 to 2. Keep that in mind. You'll see why later when we do this little matrix. If you were to go from 2 to 1, you would have used this as your origin, left and right, up and down, right? It would have been 180 plus another 90, which is 270. So it would have been 270, and your element would have been from 2 to 1, not 1 to 2. So that's kind of how you figure it out. For me, I like to just always use the smallest node. I don't know, for some reason it's just easier when you're doing the matrix, right? This would be U1, V1, U2, V2, as opposed to the other way, U2, V2, U1, V1. It's just more confusing. Well, at least for me, right? But I like to stick to the smallest node and go to the bigger node. So in this case, we're gonna stick to 90 degrees. Cosine of 90 is 0, sine is 1. Cosine squared will be 0, sine squared is 1, cosine times sine is 0. So for the next one, right, same thing. So we're going from 1 to 3, so that angle is 180. Again, if you would have used the other way, from 3 to 1, your angle would have been 0. But again, I like to go from smallest to biggest. So 180, cosine is -1, sine is 0, cosine squared is 1, sine squared is 0, and cosine times sine is 0. Finally, for the third one, going from 1 to 4, that angle is 180 plus 60, right? These 60 right here. So 180 plus 60, that is 240 degrees. Hold on, let me go and make the note. 1 to 3. And this one is 1 to 4. All right. 240, right? Take the cosine, you will get -½ Then for sine, you will get -3 over 2. Square both of them, you will get 1/4 here and 3/4 here. Multiply both of them, you will get √3 over 4, positive, because they're two negatives. Now finding the EA over L for each element. So they have the same E in the area, so that's cool, but they do have different lengths. Thankfully, we don't have to do trigonometry to find it, right? They just give it to us 2, 3, and 5. So 210 times 4 divided by 2, and then times 10 to the 5, right? Because this is 10 to the 9, this gigapascals is 10 to the -4, so it's 10 to the 5. So we're gonna have 10 to the 5 for all of them, okay? And that's all gonna be in newtons per meter. We want newtons per meter because the matrix itself is gonna be in newtons per meter. Then we're gonna multiply it by a displacement vector. You know, right? You remember force is equal to kx. Kx is a vector, this is a matrix, and this is your vector, right? So it's gonna be newtons per meter. The x is, this little x right here is gonna be a meter, so your force is gonna be newtons. So we're gonna have to convert this to, right? It's just literally a force going down, and that is 80,000. Don't get confused by the block or whatever, it's just weight. So my bad, going back, right? EA over L, 210 times 4, that's 840 divided by 2. That will give you 420. So similarly, right, 840 divided by 3, that's gonna give you 280. And again, we already multiplied GN, 10 to the -4. Then 840 divided by 5, that's going to give you 168. So cool. We could go ahead and start assembling the little matrices, right? Let's do K1 first. EA over L, right? We're using this formula now, this matrix here. EA over L for element 1, that's 420 times 10 to the 5th. Okay, now we're going to do the matrix right here. So it's going to be from U1 to U2. So from node 1 to node 2. U1, V1, U2, V2. Same thing up here, U1, V1, U2, V2. So let's bring that down. All right, so it's cosine squared, sine squared, cosine squared, sine squared, 0, 1, 0, 1. So it's gonna be 0, 1, 0, 1. Cosine, sine, negative, positive. So it's 0, 0, 0. 0, 0, 0. Same thing for that one up there. So this is 0. Negative cosine squared, negative sine squared. So it's 0, negative 1. Symmetrical, right? So that row becomes a column. 0, 0, 0. Same with this one. 0, negative 1, and 0. So cool. We got that one. Now K2. Same thing, right? Now we use this EA over L. So it's 280 times 10 to the 5th. That's gonna be open brackets or matrix, whatever. It's from nodes 1 to 3. Okay, if you would have done the other way again, you would have put, in this case, you would have put U2, V2, U1, V1. Now, just FYI, if you're just doing the stiffness matrix, that's not gonna mess you up. You'll be all right because this thing's symmetrical, right? So these 4 will just switch with these 4, but they're exactly the same, and these 4 will switch with these 4. But once you start finding forces and stresses, you're gonna get opposite signs. And just hold on before we continue. Just by looking at this, right? Just don't think of it like logically. It's not engineering, it's just logic. If you pull this down, this bar is gonna be in tension, right? You're stretching it. So this one's tension. This one, I mean, you really can't tell, right? Tension or compression, who knows? Let's just keep it tension or compression just for now. Whatever, we don't know. And this one, if you push it down, you're kind of compressing it, okay? So this one's gonna be in compression, I'm assuming. Well, I already know, right, because I already did the problem, but even then, before I started this problem, I did the same assumptions, just FYI. That's just kind of looking at it logically, okay? So just keep that in mind. So the stiffness matrix, going back, it's gonna be the same whether you go from 1 to 2 or 2 to 1, even if you do switch the angle, because if you do the cosine and sines of, if this case was 90, I think it would have been 270, remember we mentioned? So this was 270, you'll still get the same stiffness matrix and all that good stuff, but your stresses will kill you in the end if you do not follow this approach. So you need to do this if you're finding stresses or forces, just FYI. All right, my bad, going back. Cosine squared, sine squared, cosine squared, sine squared for element 2 now. It's negative 1, 0, 1, 0, 1, 0, cosine squared, sine squared. So it's 1, 0, 1, 0. This is from U1 to 3. So U1, V1, U3, V3. U1, V1, U3, V3. Close it there, close it there. All right, is it 1, 0, 1, 0, right? And then cosine, negative cosine, positive cosine, all times sine. You know what I mean? But it's 0, 0, 0. And then we got negative cosine squared, negative sine squared, so it's negative 1, 0, and then 0 here for cosine times sine. Symmetrical, right? So it's 0, negative 1, 0. The rows just become columns. Cool. So that means that's our next one. K3, finally, the last one is going to be equal to EA over L for element 3. So it's 168 times 10 to the 5th. It's between nodes 1 and 4, right? We determined 1 and 4. So now we're going this way now, U1, V1, U4, V4. I give myself some room because we're dealing with fractions now. It's gonna be a little bit bigger, a little crazier, but not too bad, right? So it's cosine squared, sine squared, cosine squared, sine squared, 1/4, 3/4. So it's 1, 4, 3, 4, 1, 4, 3, 4. Next one, cosine sine, negative, positive. So it's positive, negative, positive. Radical 3 over 4, negative radical 3 over 4, and radical 3 over 4. Okay, then this one's a negative, right? So it'll be negative radical 3 over 4. Then negative, negative. So negative 1/4, negative 3/4. And rows become columns, so this is radical 3 over 4, negative 1/4, negative radical 3 over 4. This becomes a negative radical 3 over 4, negative 3/4. And this is radical 3 over 4. All negatives, all negatives, all positives, all positives. Cool. All right, so that means we could go ahead and start assembling the big global equation, right? Force is equal to kx. But before we do that, first off, we can't even add these matrices. Well, why? It's because they don't share the same stiffness value outside. So this is 420, 168, and 280. And they're all 10 to the 5th, right? But we cannot add these unless they're all the same. So this is what we do. Before we start, because look, think of it this way. This is an equation, right? It's something is equal to something times something times something. So let's go ahead and just give them dummy values, right? So let's go ahead and put z is equal to, let's put 2, right? 2 is 420 in this case. The 10 to the 5th is x, and this is y. So this is what it looks like right now, right? 2x times y. Well, that's the same as just saying z is equal to x times 2y, right? It's the same thing. You're going to get 2xy for both cases. So that's kind of what we're going to do here. Check it out. We're going to put this 420 and multiply it to the whole matrix instead to get rid of it here. But well, we could do that now, right? But it's going to be a lot of work to do for every single number, especially here. So what we do is first we apply the boundary conditions. U2 V2 is fixed, U3 V3 is fixed, U4 V4 is fixed. So anything U2 V2, U4 V4, U3 V3, they're all gone. And same for the rows. So all this stuff is gone. We don't care about it. It's fixed. It's not going to affect us in any way once we do the calculations. Yeah, I mean, you could do it the long way and add them all up and then cancel them later, but that's just suicide at that point. So now we only care about these numbers. These 4, and these 4. Again, just throw it in there, right? So in this case, we're going to throw in 420. So 420 times 0, 0, 0, 0, and this becomes 420. I was just lazy. Now we're done here. We erase it. Okay? So now we just have 10 to the 5th outside. Same thing here. 280, multiply it here. So we're gonna, how can I do this? 280. Make it look nice, right? I don't want to erase. Whatever. It's cool. So that becomes 280, 0, 0, 0. Well, you multiply it to all of them, but all these are 0. And then finally, 168 to these 4. If you do it to 1/4 and 3/4, what are you going to get? We are getting 42, and we are getting 126. Then you multiply it to these here. Radical 3 over 4, right? Sorry if the camera's shaking. My setup's not the best. This becomes 72.75. Same with this one, 75, right? And this goes away. So now that we all have the same, they all have the same value for stiffness on the outside, we could go ahead and add the insides. So let's go ahead and do that, right? This was step 1 here. This was step 2. And finally step 3, right? So we got force 1x, force 1y. It's going to be an 8x8 matrix. This thing is going to be, well, it's not complicated because a lot of this stuff canceled out, but it's still pretty big. Okay, let me move it up in case you can't see. And I know I have a problem of not moving it up, but I mean, as long as you could follow what I'm saying. And at the end of every video, I always show the full paper at the end of right, just to make sure you didn't miss anything. 10 to the 5th, right? All of them, we're making them big matrix now. Oh man, this thing's huge. All right, so we got U1, V1, U2, V2, U3, V3, U4, and V4. Same thing here, right? We got U1, V1, U2, V2, U3, V3, U4, V4. I'm kind of speeding through it because the videos get pretty long, just FYI, but I'm just writing down what you should know, I'm hoping. U1, V1, U2, V2, U3, V3, U4, V4. All right, cool. So again, right, just like we did earlier, we're gonna apply the boundary conditions. If not, you would have to add the whole matrix. It'll be super crazy. But U2, V2, U3, V3, U4, V4, they're all 0. They're all fixed boundary conditions. So I'm gonna go ahead and do that, right? Cancel all the rows and columns. Let me go this way. Try to stay as neat as you can, you know, never hurts. And less room for error if you mess up, or if you're close to messing up. Okay, so cool, we only care about these 4 positions, right? U1, 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 V1, V1, U1, V1, V1. And these are the ones here. I like to cloud them. I mentioned it in the other videos too, just to make sure I don't miss them, because like, again, especially if you're sloppy or whatever, you might be able to just miss one. And here they're pretty straightforward, they're all grouped together, but I remember down the line, when you start including moments and forces and all that good stuff, they're kind of scattered, but always cloud them just to make sure. So cool, add all the U1 U1s. So this is 0 here, 42 here, 280 here. If you add it, you will get 322, okay? If you add the U1 V1s now, 0, 0, and 72, 75, you will get 72, 75. Cool, right there. Same thing for this one, right? Now 0, 72, 75, 0. That's another 72, 75, and finally 420, 126, 0. That will give you 546. Move it up. All right, cool. One more boundary condition, right? We got to apply the force. The forces we know at node 1. Let's see, what do we got at node 1? We got 0 in the x direction, so this is going to be a 0. And then we have negative 80,000 in the y direction. And you want it in thousands. You don't want kilonewtons because, again, newtons meter, and a meter. So we want this here in newtons, negative 80,000. Okay. So cool, that means we could go ahead and start assembling the equations. So we're gonna have, I'm gonna say it out loud and then we'll write them. So it's 0 is equal to 10 to the 5th, open parentheses, 322 U1 plus 72.75 V1. That's the first equation. Now the second one is negative 80,000 is equal to 10 to the 5th, open parentheses, don't forget that 10 to the 5th, open parentheses, 72.75 U1 plus 546 V1, okay? So let's go ahead and write that down. Actually, I should have wrote it down, save more time, but. So we got, my bad, just, this is pre-written just to save time. I know these problems are long. Step 4, we got 0 is equal to 10 to the 5th. That's gonna be 322 U1 plus 72.75 V1, okay? This is equation 1. Next one is negative 80,000, 10 to the 5th, 72.75 U1 plus 546 V1. And this is equation 2. All right, so using equation 1, there's various ways you could go about this, right? You could use equation 1 what I'm gonna do is I'm gonna isolate U1 and get it in terms of V1, so I can later plug in that U1 here and I can find V1. You could do the opposite, right? Find V1 in terms of U1, plug it in here, you'll get U1. You could even start with this equation, do the same thing. There's 4 different routes in this case. It's just basic algebra, right? So what I'm gonna do is divide by 10 to the 5th both sides, so that goes away. I'm gonna move 72, 75 to the other side, so it's gonna become negative. So you're gonna have 322 U1 is equal to negative 72, 75 V1, okay? That's from the first equation. If you do that, you will get U1 is equal to negative 0.2259 V1. That's not the answer, it's just a relationship. Now we're gonna use that to plug it into the second equation for U1 here. So you're gonna have negative 80,000 is equal to 10 to the 5th. My voice just cracked. 72.75 times negative 0.0, oh, no, not 0, 2259. 2259 V1. Then that's plus 546 V1. I just plugged in U1 in this equation, right? Do some math, you will get negative 0.8 when you divide 10 to the 5th over here. And then if you do the algebra here, you'll get 529.57 V1. Okay, if you do the math, V1, right, divide both sides by 529.57, you will get negative 0.001511 meters for V1. Then plug in this V1 into here. Your U1 will be 0.000341 meters. So that's your answers. That is the horizontal and vertical displacement at nodes 1. That's what the problem asked, right? Determine the horizontal and vertical displacements node 1. Cool, we got it. Now we got to get the stresses. And okay, so the stresses, this is how you do it. Sigma is step 7. Boom, 7. Sigma is equal to C minus matrix times your displacement vector. Your C minus matrix is just E over L, not area, right? It makes sense because sigma is independent of area. If you multiply times the area, you're gonna get a force, but this isn't the equation you use for force, so don't get confused in that sense. E over L, negative C, negative cosine, negative sine, cosine, sine. So we're gonna need E over L for each element, so we're gonna do the first element. That is E over L, 210 divided by 2, that's gonna give you 105, then 10 to the 9. We don't, not this 10 to the negative 4, it's 10 to the 9 now, okay? So it's gonna be 105 times 10 to the 9, bracket, right? That was E over L, bracket, negative cosine, negative sine. So we need those numbers. Cosine and sine, not these, okay? 0 and 1 for element 1, 0, 1. But they're negative here, so it's negative 0, which is just 0, and then negative 1, 0, 1. Then your displacement vector. So your displacement vector, we chose it from 1 to 2. So we're going U1, V1. U1 is 0.000341, negative 0.001511 for V1, right? Then U2, V2, that's 0, 0. All right, so we go ahead and do that. Sigma 1 is equal to 105 times 10 to the 9, open parentheses, 0 times the first one, negative 1 times the second one, so that's going to be a positive 0.001511, plus 0 times 0 plus 1 times 0. So cool, just that number. Sigma 1 is going to be equal to 158.66 megapascals, and since it's positive, that is in tension. Okay, so cool, we got this one. All right, we got this one. All right, next one, sigma 2. That's going to be equal to, what do we do? Get to the second element, that length is 3. So 210 divided by 3 times 10 to the 9. If you do that, you will get 70 times 10 to the 9. Open the bracket, and we care about the cosine and sines. That is -1 and 0. But they're negative here, so we're gonna have 1 and 0. Then positive, -1 and 0. I mean, what I meant was positive here, okay? So, and a positive cosine in this case was -1. Cool. So, next one, we got same thing, right? This is U1, V1, U2, V2. Now for the next one is between nodes 1 and 3, right? 1 and 3, that's why we chose that angle. So now we're gonna have U1, which is 0, 0, 0, 3, 4, 1, -0.001511. This is U1, V1, and U3, V3. Writing a little fast, a little sloppy, but just to kind of hurry it up. So yeah, right, U3 and V3 are fixed, so that's why it's 0. 70 times 10 to the 9. Then we're gonna have 1 times the first one, which is 0.000341, and then 0 times that one, which is 0, that one times that, which is 0, that times that, which is 0. So cool, just that. So sigma 2 is equal to, let's see, that is 23.87 megapascals. So it is in tension. You remember we were a little skeptical, like, is it tension, compression? We don't know. In this case, yeah, apparently X moved just a little bit, 1/3 of a millimeter, right? So when you pull this down, this one's obviously in tension, just like we expected. Here we got tension or compression, we didn't know, but now we know. So this is in tension. Now I'm gonna go ahead, and this one's compression, right? It looks like it's being compressed. So that means the next number we get should be negative. And just FYI, it is, because I already did it. So third element, right? We're going from 1 to 4. 210 divided by 5 times 10 to the 9, just E over L. That's gonna give you 42 times 10 to the 9, bracket, negative cosine, negative sine, right? So that is positive half, positive radical 3 over 2, because our signs are switching. So it is half radical 3 over 2, and then the negative half. All I'm doing for all of this, right, I'm not sure if you caught it, but it's just getting the cosine and sine, and the first ones will be negative in sine. So sometimes they were already negative, right, if you flip the page, and then the positive values here. But in this case, the positive values were negative. So that's how we got that. Finally, U1 is 0.341, negative 0.001511, 0, 0. This is U1, V1, U4, V4. Between nodes 1 and 4. Again, if you would have chose the other angles, remember, you would have had U4, V4, U1, V1. So that's why it's real careful. And if you would have done that, the signs would have switched, right? This number multiplied to a positive will stay the same. This one, same thing. But if you would have multiplied it to these now, imagine you put this one down here and this one down here, you would have had opposite signs, right, when you multiplied them. So that's why it's real important you stay consistent with the way you choose the angle and all that good stuff. So let's keep it going, right? First one times half, that's going to be 0.000341 divided by 2, right, times half. So that's going to be 0.0001705. And then the next one, radical 3 over 2 times this number right here, it's going to be a negative, right? Then you're going to have 0.001309. Close that up. Finally, do the math. Sigma 3 will be, what's that going to be? Negative 47.80 megapascals. And again, compression, right? Because it's negative. So I'm not going to do it in this video, but I did do it in the previous one, problem 329, but I'm going to get you started. So go to 329. I'll put it in the comments. Just check the comments on this video, and I'll tell you where to go in the video, on the 329 video, right? I'm gonna show you how to verify, because sometimes they ask you to verify force equilibrium. In this case they didn't, but then they would ask it at node 1. They usually ask it where all the shit's going down, right? In this case, everything's going down right here. So the way you would do that, using the stress values, assuming they didn't ask for force values, you would just multiply the stresses time each area. So sometimes there are different areas, so you just got to be careful. But look, we know 80,000 was going down, right? So that's this one. This one's in tension, it was going up. So you're gonna do sigma 1 times area of 1. In this case, the area is the same for all of them. So it's 4 times 10 to the negative 4. But again, sometimes that's not the case. For this one, it's also in tension, right? Positive. So sigma 2 times area of 2. That'll give you that force number. This one, the reason I didn't pull it down is because it's compression. So when it's compression, it goes into the node. So let me draw more arrows, right? It's going that way. And that's gonna be sigma 3. You don't do negative. You already accounted for the negative sign going into the node. So it's gonna become a positive 47.8 times area, okay? And if you do that, you'll get force number, sigma times area, right? That's Hooke's law from strength of materials or mechanics of materials. I'm not sure what you guys call it, but we call it strengths. Yeah, that's pretty much it, right? So when you do the sum of the forces in the x direction and the sum of the forces in the y direction, they should equal 0. You don't set it equal to 0. It's just they should equal to 0, assuming you did everything correctly. Now, I'm not going to do it here, but just watch the other problem and see how I do it. And yeah, that's pretty much it. And don't worry if they're not exactly equal to 0. Maybe you'll probably, in the other problem I got 15, right, for I think for x, and then like it was about 100 for this one, I can't remember. But that's okay, right? You're dealing with thousands of newtons. Obviously, we did rounding. We rounded a lot of stuff, so you're not going to get a perfect 0. And you're probably asking, well, what's a safe, like, kind of delta to have to make sure that, you know, you did the problem right? I think if we're dealing with, in this case, you're going to get like something in the 20,000s or 40,000s, right? If you do the math, this one's an 80, so I think a safe delta would be like 5,000. Anything under 5,000, maybe 7 is cool, but anything above 7, I'll probably be like, hold on, I probably did something wrong. But if you go back and you verify your steps and you didn't do anything wrong, then yeah, trust your gut. That's just a rounding error. It's kind of where your mind comes in, you know, like, is it reasonable for me? But yeah, that's the top part right there. It's the bottom part, and then there's the top part right here, and the bottom.